Alright, let's finish up the section 17.5. This will wrap up the chapter. Let me pick a pen. Okay, so this is general plane motion, and let's just imagine we have some mass, some center of mass G, and all these forces acting on it. Maybe even has some omega and some alpha. And if we're looking about G, let's actually give it a moment, maybe another moment. All of these are forces. Alright, so something's going to happen, right? We're going to have some possible omega and some alpha. In this case, about G, we would say the summation of the forces in the x direction, we get three equations, is equal to mass times the acceleration of G in the x. The summation of the forces in the y direction is equal to the mass times the acceleration of the mass center in the y direction. But then we also get, if we sum the moments about G, the mass center, we can use the moment of inertia about that spot times alpha. This gives us three equations. We can also do about some other point P if it's more convenient. This is a convenience thing. Alright, so let's say we've got, just make it simple, a moment, some forces, and there could be some XY axes somewhere, and we could be measuring from some point P on some other translating reference frame. Doesn't have to be translating, but it can be. It can be rotating too. We just didn't go over that. If that is the case, we can, let's call that point P in this case, sum the forces in the x direction. It's still going to equal the mass times the acceleration of the mass center for the x and y. And that gives us two equations. We can also get one more by summing the moments about this point P and saying that's equal to the kinetic moment, the summation of the kinetic moment about P. If you do this, then you have to do IG about alpha. This kinetic moment is IG about alpha plus whatever acceleration G has times the perpendicular distance about P. Alright, so that's three equations, and using some other point P. In that case, it's often convenient to turn this into a kinetic diagram. We would also have the weight going down. Ding. So, if I wanted to turn that into a kinetic diagram, that would look like assigning some acceleration of G in the x direction, some acceleration of G in the y, giving us an acceleration vector, and then we go ahead and say all those moments and forces, if they are not concurrent, give us some IG alpha. And let's call that G. So that is a free body diagram to a kinetic diagram. Pretty useful. And let's look at one more thing. What about the instantaneous center? So, summation, oh, that's not a moment. The summation of the moment about the instantaneous center is equal to I about the instantaneous center times alpha. And that's the same as the summation of the moments about O is equal to IO about alpha. And so let's look at this is the case where we would have a wheel rolling without slipping. So it has some motion, some mass center. We'll call this A as our instantaneous center. G is going to have an acceleration in the x direction. It's not lifting on off the ground, so G will not have an acceleration in the y direction, but it has a mass times gravity pointing down and a normal force pointing up. So we're going to turn this into a kinetic diagram. If this has some rolling power to it, some moment, let's pretend in this case it's caused by a frictional force, like the rubber in the concrete in the road. We can turn this into a kinetic diagram where we get some mass times the acceleration of g. I'm going to draw this distance out d. This is our perpendicular distance from A and our instantaneous center, right, of 0 velocity. And for our kinetic diagram, we also need to include I, G, alpha. Okay, so if we have two choices in this case. If summed about G, we would just do the summation about G, the moments, is equal to I, G, alpha. Alright, but if summed about the instantaneous center, then we can say the summation of the moments about A in this case is equal to the I about A times alpha. Well, most people don't know what I about A is, so we would say the summation of the moments about A is equal to this I alpha for G, the mass center, and then we add on the kinetic moment at the perpendicular distance d. Alright,